In this video, we are going to demonstrate how to solve for the surface area of a sphere. Basically, you're deriving the formula for it. Parts of this are not immediately available to you, nor were they described in the text, but we'll guide you through as we go along. Okay? So first, we assume that we have a sphere. Okay? So we're just going to draw a circle as a representation of the sphere, going all the way around, hopefully making a good sphere. Okay, so we have a sphere, okay, with a center point. Okay. We are actually going to examine only a portion of this, say this piece right here. Okay, I have drawn it a lot bigger than I would normally want, okay, but it'll suffice. Okay. So we have basically what's known as the frustum of a cone. One of the problems you have deals with frustums, okay, just in case you wish to look it up. But it's basically the bottom of a cone that has had the top kind of cut off. Okay. It looks like that. Okay. And that's the piece that we are referring to right here. Okay. So we have the length along this slant is L, and then we also have a height, h. Okay, so this is kind of like the trapezoid. And in order to find the surface area of it, remember it curves around, it's not quite the area of a trapezoid. The area of this entire ring is given by the middle value of these guys, okay, which is just going to be the circumference of a given ring. So whatever ring we choose, we're choosing this particular ring. But if we were to move down further, we'd have a different circumference. The area of that ring is our circumference times our slant height, not the vertical height as it would have been if it were a flat figure. Okay. Remember, this is a three-dimensional figure, so it's slightly different. Okay. So when we do this, we can also note a couple things. One, the distance to the center of the circle, to any one of these points, really. Okay, we're actually going to draw it to where that center is r. It is the radius of the circle. Okay. The distance away, okay, from there, we're just going to call x. Okay, it is some distance away. But there's an inherent relationship here. Okay. The first piece is that this triangle and this triangle are similar. Okay. And we can show that more precisely by recalling that this is a tangent line. Okay. A tangent line is perpendicular to this guy. I'm actually going to just shift the triangle over, where if the height is here and the length is along the hypotenuse, you have x, you have r, you have L, and you have h. Okay. This is a right angle, as is this guy right here. Okay. But we also have this as being alpha, this as being just beta. We're going to call those, and they are complementary. Okay. But we also know that this must be complementary to A, because if there's a total of 180 degrees here, we lose the right triangle, we only have 90 left. Alpha plus something else is 90. That means that beta is also here. Since it's a right triangle, we also know that we've got that. So we have two similar triangles, which means that we can write the relationship L over H, okay, the hypotenuse over the side across from alpha is going to be the same as writing the hypotenuse of the other triangle over x. Okay. So the area of the ring then is just given by our circumference at that particular ring position, okay, times L, which is equal to 2 pi x. That's the circumference. Remember, the circumference only goes out to here, times our length. Our length, if we rearrange this equation, is L is equal to RH over X. The area of that ring then, just that ring, is equal to 2 pi RH. Okay? But what does this remind you of? This should remind you of basically just a cylinder. Okay? This is the cylinder equation. If you know the circumference around plus the height it goes up, you know the area. But this is true for any size cylinder, which means it's true for a cylinder that completely circumscribes in 3 dimensions the actual sphere. Okay? Basically, the outer surface area of the cylinder is the same as the surface area of the sphere, based on this reasoning. So, because we haven't actually specified what's the inherent relationship between L and H, it doesn't matter. We don't need to know a particular number for these. This was a general prescription. So we now have the area of the sphere is equal to 2 pi RH of the same cylinder that encapsulates. Well, how tall is that cylinder? Okay, the cylinder, I'm going to write that over here, the height of the cylinder is equal to twice the radius. You go down 1 and up 1, 2r. Okay? So the area of the sphere is equal to 2 pi r times 2r. Okay? This is equivalently, and our final step, 4 pi r squared, which is the well-known area for the surface of a sphere. Okay? Again, this is not a rigorous proof, but this is a, by visual inspection and by reasonable assumption, we can take what the area of the sphere actually is.